So in this video we are going to talk about the question which appeared in thermal and statistical physics in JEST 2013 examination. So let's continue with the first problem. The statement is, for a diatomic ideal gas near room temperature but fraction of heat supplied is available for external work if gas is expanded at constant pressure. Okay, so at constant pressure, the work done, that's delta W, that's given by P delta B, or this is equal to NR delta T. Okay, well, it's the ideal gas. Okay, so let's call this as equation 1. Also, during this process, let's assume that delta Q be the heat exchange. Okay, the heat exchange during this process, let's call this as delta Q, and that is equal to NCP delta T. So let's call this as equation 2. So basically we have to evaluate the ratio between delta W and delta V. So that will give us the fraction of heat which is available for external work done. Okay, so that means we are asked to evaluate what is delta W by delta Q, and that is equal to NR delta T divided by NCP delta T, and that's nothing but it's the ratio between R and Cp. Okay, so let's call this as equation 3. So now we are given a diatomic gas molecule. Okay, so we must have an idea about the Cp for the diatomic gas molecule. So this we can evaluate by recalling the idea of the degrees of freedom. Okay, so for diatomic gas molecule we are having translational degrees of freedom. Okay, F of T, that's a translation degrees of freedom, that is equal to 3. Okay, and then the corresponding rotational degrees of freedom are 2. Okay, so that means the average energy per gas molecule E1, that is equal to the total degrees of freedom are 5 at ordinary temperature, so 5 by 2 kVT. So that's the average energy per gas molecule at ordinary temperature. So per mole the corresponding energy will be 5 by 2 Na kBT. So with Na, that's the Avogadro number. Now we are calculating the average energy for Avogadro number of molecule. Okay, Avogadro number. So this is equal to 5 by 2 RT. Okay, so from here, from the average energy, we can calculate the Cv per mole, the heat capacity per mole, and that will be equal to dE by dt, and that is equal to 5 by 2 R. Okay, so therefore Cp, that is equal to Cb plus R, and that is equal to 5 by 2 R plus R, and that is equal to 7 by 2 R. Okay, so therefore now Cp is known to us. So from equation 3, delta W by delta Q, that is equal to R divided by Cp, which is 7 by 2 R, that's nothing but 2 by 7. So therefore option D is the correct one here. So let's continue the next problem. The statement is, two drunks start out together at the origin, each having equal probability of making a step simultaneously to the left or right along the x-axis. The probability that they meet after n step is how much? Okay, so here we can make use of the expression that we learned for the random walk problem in one dimension. So here for the given situation we are having P, that is equal to Q, that is equal to 1 by 2. So that's the probability of taking a step towards right or left. It's the probability is same in both cases. Okay, so now the probability that they meet after n step is how much? Okay, so that means we are having two different random walker, and each random walker is taking n steps. So the total number of steps will be, total steps is equal to, let's say capital N, and that is equal to n plus n, because each random walker is taking n steps. Okay, now the point is that if we just recall the final result that we learned for the random walk problem in one dimension, where n1 steps were along right and n2 steps they were along left direction. Okay, the corresponding probability was Wn n1, that is equal to n factorial upon n1 factorial steps, n1 steps of one kind, and then remaining n minus n1 factorial of another kind, and then p power n1 and q power n2. So this was the result that we obtained. Now here, according to the situation, so we are having two persons which are starting their journey from a fixed origin. Okay, and then each of them is taking n steps. Okay, so it's not necessary that they can move in either direction, along the right hand side or left hand side, but the point is that after making n step, each person is supposed to be at the same position here. Okay, here. Okay, so this is only possible when this n, it is the number of steps which are taken by the individual random walker, that is even. That's only possible when this is even, because when this small n it's odd, so then it's not possible for the random walker to be exactly at the starting position. So that point is clear. Okay, so that means the n, both n, they are even. So when we add these two even number, again the capital N, it's going to be an even number. Okay, so let's see what is the corresponding probability. So W, that is equal to capital N, so that is equal to small n plus that's twice n, so that is equal to capital N factorial divided by small n factorial. Okay, and then n minus n factorial, and then p power n1. So p here it is 1 by 2, that is 1 by 2 power n1, which is n, and then q, which is again 1 by 2 power n minus n1, which is 2n minus n, so that is again n, small n. Okay, and this can be rewritten as 2n factorial divided by n factorial, and n minus n is again n factorial. Okay, and then 1 by 2 power n plus n, that is 2n. 1 by 2 power 2n. Okay, and this will comes out to be equal to 2n factorial upon n factorial its square and 1 by 2 power 2n, or this can also be rewritten as this is equal to 2n factorial upon n factorial square 1 by 2 power 2n, this is equal to 1 by 4 and its power n. It's the same thing. Okay, so therefore option A is the correct one here. So let's continue with the next problem. The statement is, a metal bullet comes to rest after hitting its target with a velocity of 80 meters per second. If 50% of the heat generated remains in the bullet, what is the increase in its temperature? Okay, so here when the bullet hits the targets, so there will be a complete conversion of the kinetic energy into the heat basically. So it's given that it's only the 50% energy that is converted into heat. Okay, and then we have to find the corresponding change in the temperature of the bullet after the after hitting the target. Okay, so the kinetic energy of the bullet, kinetic energy is equal to 1 by 2 m v square. Okay, and this is converted into heat, and it's only the 50% of the energy which is associated with the bullet after hitting. Okay, so that means, so 50% of kinetic energy that is converted into the heat which is associated with the bullet. Okay, so let's say corresponding change in temperature of the bullet is delta T. The remaining energy is associated, the remaining 50% energy will be associated with the object into which the bullet has entered. Okay, so that means, so 50%, so that means it's 1 by 2 of the kinetic energy into 1 by 2 m b square, that is equal to m its specific heat and the corresponding change in temperature delta T. Okay, so m will cancel with m, the corresponding change in temperature of the bullet delta T, that is equal to, so it is 1 by 2, not 1 by 4. Okay, so delta T is equal to v square upon 4c. So b square, that is 80 into 80, that it's in meter per second, divided by 4 into the specific heat, that is given as 160 joule per kg per degree Celsius. Okay, so after solving it, we obtain the corresponding change in temperature, that is 10 degrees Celsius. So therefore option C is the correct one here. So let's continue with next problem. The statement is, consider a particle with 3 possible spin states, S is equal to 0 and plus minus 1. So there is magnetic field H present and the energy for the spin state is spin state S is minus Hs, that's the interaction energy. The system is at a temperature T. Which of the following statement is true about the entropy St? So S as a function of temperature. Okay, so it's given that the possible spin orientation are plus 1, minus 1 or 0. Okay, and the interaction energy is given as minus H multiplied by S. So this way we obtain three interaction energies, and what are those? Minus H into, so the first is minus H and then into S is plus 1, so in that case it's minus H. Okay, in the second case minus H into minus 1, so that will give us the interaction energy H, and in the third case it's minus H into 0. So okay, so this way we obtain 3 different states, one with energy minus H, then 0 and H. So okay, so at a non-zero temperature, so it's possible that all these 3 spin states, okay, so spins may occupy maybe in any of these 3 possible spin states. Okay, so therefore the corresponding value of omega is 3 when temperature is not equal to 0, or it's a non-zero value. Whereas at absolute 0, at T is equal to 0 Kelvin, where the thermal energy that diminishes, so in that case the system will exist in a new configuration in the ground state corresponding to omega is equal to 1. Okay, so therefore S when T is equal to 0, that is equal to kb ln omega, and that is equal to kb ln 1, and that is equal to 0. Okay, this is the situation when temperature is absolute 0, whereas when temperature it's not equal to 0, it's having certain non-zero value, the corresponding value of the entropy will be ln omega, and that is equal to kb ln 3. Okay, so therefore option D here is the correct one. So let's continue with next problem. The statement is, consider 3 situations of 4 particles. So we are given a set of 4 particles, n is equal to 4, in one-dimensional box of width L. So we are given a one-dimensional box whose width is L. Okay, let's say it's a one-dimensional box, okay, with hard walls. In case 1 the particles are fermion, in case 2 they are boson. So we are having 3 different cases, one of fermion and second of boson, and in the third case they are classical particle or distinguishable particle. The total ground state energy of the 4 particles in these 3 cases are EF, EV and E classical respectively. Which of the following is true? So let's see. So the energy of a particle in one dimensional box, that is given by E, that is equal to n square h square upon 8m L square. Okay, so that where n can take value from 1, 2, 3 and so on. So for n is equal to 1, we obtain the ground state energy. So that means E1, so that will give us the ground state energy. So that is equal to h square upon 8m L square. Let's call this as E0. Okay, so let's mark this as E0. Okay, so now for n is equal to 2, we will have its n square. So that means we will have 4 times E0. So here let's mark this somewhere here. That is 4 times E0. So this is E1, E2, and then similarly we will have E3, and then we will have E4. Okay, so E3 will be 3 square times E1. Okay, so E3, from here I can write E3, that is equal to 9 times E0, and E4, that is equal to 4 square, that is 16 times E0. So this is 9 E0, and this corresponds to 16 E0. So similarly we can get an idea about the energy level, higher energy levels. Okay, now the question is, let's try to understand the case 1. It's a system of 4 fermion. Okay, so assuming these levels to be single particle state, so then we can put these fermions like this. Okay, so that means the total energy for the system of fermion will be that is 16 E0 plus 9 E0 plus 4 E0 plus E0. Okay, so this will be 16, 9, 25, and then 29 and plus 1 E0, so that is 30 E0. So when it's a system of fermion, so EF, that is equal to 16 E0 plus 9 E0 plus 4 E0 plus E0, so and that is equal to 30 E0. In the second case, when we treat the particles as boson, so the ground state energy, because we have to make a comparison between ground state energy. So for fermion, we can put all the particles in the ground state with energy E0. So we can substitute all boson here. Okay, so the corresponding energy for a system of boson will be EV, that is equal to 4 times E0. Now for the third case, when we treat the particle as classical particle, so in that case there is no condition on the occupancy of the particle in a particular energy state. We can put all the classical particle in the ground state. Okay, so that means again for the classical particles also the ground state energy is 4E0. So therefore from here we notice that a fermionic system will have the largest energy, and then for bosonic and classical system the energy is same. So from here we conclude that option B is the correct one. So let's continue with the next problem. The statement is, if the distribution function of x is given as fx is equal to x exponential minus x by lambda over the interval 0 to infinity, the mean value of x is. So here we will apply the definition of determining the mean value once the distribution function is given to us. Okay, so here we are given the distribution function in terms of x as fx, that is equal to x exponential minus x by lambda. Okay, so and this is valid for the interval 0 to x to infinity. Okay, so now by making the definition of the mean value, so mean of x, that is equal to 0 to infinity x fx dx divided by 0 to infinity fx dx. Okay, so then substituting the value of fx here, so this reduces to x square and then exponential minus x by lambda 0 to infinity and then dx divided by 0 to infinity exponential minus x by lambda, but also x here. Okay, dx, and let me call this as I1 divided by I2. Okay, so let's call this as equation 1 and this as equation 2. So now let's try to first solve I2. Okay, so I2 that is equal to 0 to infinity x exponential minus x by lambda dx. So we can solve this by integration by parts, and when we do that, so that's first into integral of second exponential minus x by lambda divided by minus 1 by lambda, okay, 0 to infinity, and then minus integral of derivative of first, integral of derivative of first. So the derivative of first, that's 1, and then integral of second exponential minus x by lambda upon minus 1 by lambda dx. So upon substitution of the limits, so this expression will reduces to 0. So we will be ultimately left with the only the second term here for the evaluation of I2. So I2 will be, that is equal to, minus and minus will become plus, so lambda 0 to infinity exponential minus x by lambda dx. Okay, so that is equal to lambda and then exponential minus x by lambda upon minus 1 by lambda and from limit 0 to infinity, and this will comes out to be equal to minus lambda square. Then if you substitute the upper limit, that's exponential minus x by lambda, when x goes to infinity, that will be 0, and then lower limit will give us a factor of minus 1, so that is equal to lambda square. So let's call this as result 3. Okay, now we can evaluate the I1 that is equal to 0 to infinity x square exponential minus x by lambda dx. So that is equal to first into integral of second minus x by lambda upon minus 1 by lambda, and then from 0 to infinity. So minus integral of derivative of first, so that is 2x from 0 to infinity, and then integral of second, so that is exponential minus x by lambda upon minus 1 by lambda dx. So upon substitution of the limit, so this will reduce to 0. Okay, so you can cross check it. Okay, so this minus and minus will become plus, so ultimately the second term, that is this one, this will give us a factor of 2 lambda and then 0 to infinity x exponential minus x by lambda dx. So this part we have already evaluated in equation 3. So this is equal to lambda square. So therefore I1 is equal to 2 lambda cube. So that means the mean value of x, that is equal to I1 by I2, and that is equal to 2 lambda cube by 2 I1 is 2 lambda cube and I2 is how much? I2 is lambda square, lambda square. So that means that is equal to 2 lambda. So therefore B is the correct option here. So let's take a look at the last problem. The statement is, consider a uniform distribution of particles with volume density n in a box where particles have an isotropic velocity distribution with constant magnitude v. The rate at which particles will be emitted from a hole of area A on one side of this box is, okay. So this is almost identical to to say that that's the total number of collision. So here we are making an argument that total number of collision, let's call that NC, total number of collision which occur or that occur per second on a wall, okay, or this is equivalent to say all the particles which emerge from a hole of area A. Okay, so that means the number of particles which are emerging from a hole of area A. So that's all. That's equal to the total number of collision NC which occurs per second on a wall whose area is A. Okay, so on a wall whose area is also given by A. Okay, so these two statements, they are equivalent. So here basically what we require is, we require the one dimensional probability distribution, which is given by f of Vx, okay, that is equal to m upon 2 pi kt. So this result we discuss in Maxwell-Boltzmann velocity distribution. So this power 1 by 2 and then exponential minus m Vx square upon 2 kt, because we are only considering the particles which are moving along the x direction. Okay, so let's call this as equation 1. Okay, so here we consider only the particles which are moving along x direction. Okay, so only particles moving along x direction with velocity Vx. Okay, now the number of particles with velocity Vx, now we are going to calculate the number of particles with velocity Vx, okay, and colliding with the wall, which are colliding with the wall per unit area and perpendicular to Vx. So that means if this is the direction in which particles are moving, so in perpendicular to Vx, that means they are hitting the wall directly. But now we have it's per unit area, so those numbers, they will be proportional to, if we denote those number of particles as NC Vx, okay, that number will be proportional to the number density of the gas molecule and then the area where they are hitting. Okay, and then that's also proportional to the velocity with which they are moving and for what time duration they are hitting. Okay, or if we call this as equation 2, so that means NC total, okay, so that is equal to N A dt, okay, and then the distribution, this function 0 to infinity Vx, and then that probability distribution function f of Vx and dVx. Okay, so that means and remember that here we are only calculating the particles which are moving in the positive x direction. So that's why the limit of integration, they range from 0 to infinity. Okay, 0 to infinity, because we are considering only the particle, because only the particles moving in positive x direction will hit the wall, or they will emerge from area A. It's a same statement basically. Okay, so now the collision flux, we want to calculate the collision flux. Okay, so we are defining another term, collision flux, that is the number of collision. So it means the number of collision per unit area and per unit time, okay, that is the rate at which particle will be emitted. So this is equivalent to, that is the rate at which particles will be emitted from area A, so that flux, okay, that is equal to NC total, the total number of particles which are hitting or merging, and upon area A, okay, and then dt per unit time. Okay, so that is given by, so NC, so from here let's call this as equation 3. So from equation 3, so we can evaluate this result NC upon A dt. So we will be left with simply the number density and then 0 to infinity Vx f of Vx dvx. So let's call this as equation 4. Okay, so let's move to the next page. So this expression, this is equal to, so phi that is equal to, now we are substituting a value of the fvx n and then 0 to infinity and then vx, then f of vx, which is equal to m upon 2 pi kt. Remember k here, it's a Boltzmann constant and its power 1 by 2 exponential minus m vx square upon 2 kt multiplied by dvx. Okay, so here we can take this m upon 2 pi kt term outside and then we will make use of the result here, that 0 to infinity x exponential minus alpha x square dx, that is equal to 1 upon 2 alpha. So here x is bx and exponential minus alpha x square, it's this one. So here bx is the variable. Okay, this is a constant, so this will come outside. Okay, so this comes out to be equal to n m upon 2 pi kt. This is slightly bit lengthy problem, 1 by 2, and then the we apply the result, which is 1 upon 2 alpha. So 1 upon 2 alpha, so alpha is m upon 2 kt, so this will become m upon 2 kt. Okay, so this upon solving, it will give us n and then kt upon 2 pi m and its under root. Okay, and this can also be rewritten as this, the final result. So I'm talking about this one. This can also be written as n into, so I'm multiplying with 8 in the numerator, 8 kt upon 16 pi m and its under root. So this is equivalent to n upon 4. Okay, 8k, it's a Boltzmann constant, k is a Boltzmann constant, upon pi m and root, or this is equal to n by 4 and v average. Where v average, we have replaced v average, that is the expression for the average velocity, 8 upon pi m. Okay, so therefore if we just take a look at the option, the right option is, this is n by 4 into n by 4, the rate at which particle will be emitted from a whole of area nb. Yes, this one, the C1, option C is the correct one here. So it's the result that we obtained, it's n by 4 v, because here it's because of the region, because the way we define the flux, it is okay, so equation 4, from equation 4, so this one, this part, because we have taken this a in the denominator, so by taking a to the other side, so a will come there. Okay, so that completes the solution.